Afternoon, everyone. This afternoon's talk is on UVM-AMS, which is a standard that has been worked on for, say, about 4 years, but really until about last year did it get any momentum. And that momentum happened between Stephen and myself actually just spending a bit of time writing some code and filing it as an example. So Stephen can't be here today, he's actually online. Stephen is a member of the technical staff in Renesas. He's been there, I think, for over 10 years, sits on the UVM committee and has for many years, and is also on the UVM-AMS one, and is sort of our in-house expert on UVM. Myself, I'm a distinguished member of technical staff, based out of Edinburgh. I sit on the UVM-AMS committee, chair of the System Verilog AMS one, and my sins I'm dragged into the System Verilog ones as well. It sounds great, but after a while you get fed up of these meetings that you're asked to do work for. And part of the reason the UVM-AMS is slow is most of the time the vendors will help a bit, but when it comes to documentation, it's up to pundits like me to do the work and take second place. So, please work. Could you get next for us? Right, that's working. So we're just going to cover why we need UVM-AMS, and we're calling it MS because it's not really just for AMS. It's designed for real number modeling, or DMS, as some people call it, as well as AMS. The talk today is really going to focus on the AMS part because that is the most restrictive part of it. So things like how the AMS simulators work. Yeah, you click a button, the cadence tool works or the synopsis tool works, but there's a lot behind the scenes that you need to know about. DC operating point, transient behavior. Then we're going to go on this concept of a UVM mixed signal bridge, which is really the crux of how we get UVM working in a real number AMS setup. Stephen will go through some of the UVM mixed signal phasing. So we haven't changed the phasing. I'm not a UVM expert. Then we'll go through the messaging. Just on that note, if you get someone who claims they're a UVM mixed signal expert, they're lying. There's no way you can be like an Andrew Beckett on mixed signal stuff and someone like Steve Hobbs on UVM. You know, be great, but it's just too much for one person, I reckon. So over to you, Stephen.
Thanks, Peter. So just going through the rationale of why, what's the driver behind the UVM-AMS working group standardization. So obviously what we want to do is we want to take, our industry standard metric-driven verification and move it into and extend it into the realm of mixed signal. The committee is there, or the working group is there to try and standardize on the way that we would essentially the appendix to the UVM to allow it to become more mixed signal aware, so that we get all the benefits of constrained random verification applied to analog and mixed signal designs. So as Peter said, the committee was originally called UVM-AMS, but the focus is actually any mixed signal system such as DMS, real number modeling, SPICE, or a mixture of any of those sort of abstractions. So that's why I think rightly it's UVM-AMS. So, the sort of typical verification objectives that the constrained random allow you to do for mixed signal would be sort of analog performance, checking that analog performs under a large set of digital configurations where connected to a digital system, control system, interactions between analog functions, sort of feedback loops, and all these sort of things where you need to cover corner cases, dynamic control, and finding problems with the, typically we're using UVM mixed signal to find problems with the A to D interaction. So one of the discussions that we keep having with some of the more kind of analog or mixed signal traditional verification groups is that they seem to be a little bit frightened by the concept of randomization. So the randomization isn't actually mandatory. We those coming from a DV background would understand what the benefits are, but even if you don't go for the full randomization, the benefits are that the guys can then use the standard methodology and they can reuse our existing UVM components we've developed for the digital world, and all of the other additional benefits you get from debug and messaging from UVM. So I think next one, thanks Peter. So the requirements from the UVM-AMS working group DoD document, sort of summarized, is here on this sort of slide here. So as I said before, the concept is to apply UVM methods and techniques to AMS circuits, whilst allowing DMS and real number modeling to enable a single test bench environment to work, whether it's using any of those abstractions of the DUT, and to be able to describe a methodology which takes existing digital UVM components and allows you to readily extend them with the minimum of fuss to then allow you to use with the mixed signal physical layer. Also to allow coordination of stimulating, measuring a signal as you would in the traditional UVM mechanisms of using sequencing and monitoring and all the things you'd find in a normal UVM agent. It needs to be independent of the abstraction layer of the AMS signals. As we've said before, it needs to support all these different abstractions, and also to eliminate the need to rely upon conversion elements to change the abstraction level of the DUT. So allows you to have your control over how you're doing that. But crucially, it needs to use the language standards as they are today. So that's why you'll see we've come up with a scheme which obviously has some kind of bridge in it to bridge between the different languages, because we don't have the capabilities within all these different languages sitting on the analog and the SPICE simulator and the digital simulator. We have to make some jump through a few hoops to make it all work together, and simply because you might be waiting years for language standards to evolve to a point where we don't have to do any of these things. Thanks, Peter. So I think now I'm handing over to Peter, because he's going to talk about some of the realities, some of the details of how the Verilog AMS simulator operates, communicates with the digital world.
Yep. Okay. Cheers, Stephen. Yeah, just as an example, System Verilog AMS started, I think, about 2008, 2010. Yeah, we're still not getting there. Even as chair, it's just banging a brick wall. So there's no point of saying we'll use System Verilog AMS, because it'll be 2030 maybe. Right, the AMS simulator, it's really important when you're doing mixed mode simulations that you understand how the analog and the digital interact, how initialization works, because UVM does a lot of stuff during the build phase at time zero. You've got an analog solver doing this. If you know the sequencing, you can get it perfect. If you don't, you might go, it was working, now it's not. So we need to know the sequence that variables are assigned, processes are executed, and this is to avoid race conditions. What you don't want is to run a sim and find that a variable's queried an analog one at time zero, and one run it gets a result, and another run it doesn't, just because a process is started up in a different order. Because there's lots of things in the System Verilog language that say it is indeterministic. Knowing the effects of DC operating points on certain AMS filters, so there's a transition statement, there's cross above, these are, and there's Laplace. Knowing how they work at DC operating point, and if you skip them, exactly what that does. It's basically don't skip it, because it's vendor specific, as I learned badly. No one can remember every part of an LRM. There's so much to it. What we want to do is enable the UVM dot to be reconfigured before DC operating point. So this is like you've got a cap, you've got a resistor there, but suddenly you want the resistor to be open for this simulation, or the cap to be a different value. So there's techniques that you can do that during the build phase of the UVM that allow you to change the value before DC operating point. So it's a neat trick. Yeah, and stuff for debug. Again, from experience, if you get convergence failure or DC operating failure, you've got nothing in your waveform file. The simulators, none of them really give you anything useful. So you need to have something that prints out loads of garbage to the screen that hopefully will give you a hint. And please don't use #0. I see people do that. In fact, I've even seen a vendor put that in their tool to fix something. So definitely don't do that. That really means you don't understand what's happening. Yeah, and Stephen and I found you must remember to raise a UVM objection before DC operating point, otherwise nothing happens. So what happens is you've got your code, and at all variables are at declaration will get an initial value. So if you don't declare anything, it will take whatever the default is. So in AMS, a real number will take 0. You can also declare it with an initial value. You can instantiate a class and call the new constructor. After it's done all of that, it passes control over to the analog initial block. This allows you to do some neat tricks. There's analog node alias, analog port alias that basically allow you to connect things further down the hierarchy to another net. There's a few other things you can do in there, but keep it simple. You'll break tools. After that, or actually just in the analog initial block, because they can't do out of module references, the order that the analog initial block is triggered in doesn't matter. But when it passes it to the digital control, all initial blocks can be executed at any order. So you need to make sure that whatever you do in the digital domain, it's robust and it doesn't rely on this initial block firing first and then this one. Most tools tend to follow it on the order that's in the module. So if you've got 2 initial blocks, it'll do in sequential, but there's no guarantee. And basically, the initial blocks will process until they start to consume time. The point it starts to consume time, the control's handed back to the analog solver, and the solver will now then go and try and get the DC operating point for the analog circuit based on the digital values. Now, hopefully your digital values are static and it will get it very quickly. Sometimes they're not, and it's an iterative process. So the best way of doing this is making sure all your analog nets are 0 volts at time 0. You'll get a DC operating point within seconds. Even on some of our biggest chips, I've got it down to about 60 seconds. You look worried, Andrew, but
just most people don't actually do that.
No, they don't. Yeah.
Is that a safe thing to do if many of your nets are not, you know, and sometimes in digital the nets that go to the analog are not initialized at time 0. Or that are X.
They're X, so your connect module will probably convert that, and if it's got a voltage supply that's 0, that X will go to 0. So
yeah, okay,
you're safe.
Okay,
yeah. Okay. Now, digital guys don't like this, but actually the analog solver is in charge. So the people that give you the most grief are actually in charge. So what happens is the analog solver goes, I think I can go that far in the future for a time step. It'll go and do all the maths. It hands control back to the digital guy and goes, please be friendly with me. He comes along, then goes, I'm going to make a digital event, which changes something in the analog. So the poor analog guy goes, great, I've done all that maths. I'm going to log the whole lot in the bin, and I've now got to do it again. So digital to analog events are very costly. So
Anglo civilizers used to throw stuff away, though, so that's okay.
Yes. But I'm thinking of my hand drawing it myself, I would be annoyed. So from the analog, it will then again advance in time, and this time the digital has advanced the same time step, so it's all happy. So things to take into account, you know, analog engine always leads. Your digital will never exactly match, although I've got it as T2 there. The T2 in the analog has 32 or 64-bit resolution. Your digital has 1 femto, so it'll snap, you know, to the closest 1 femto. Most simulators will monitor any digital signal that goes into the analog and treat that as a digital to analog event. Sort of things I do see people do is back annotate SDF in AMS. What does that do? It means all you've got your loads of digital outputs that are all skewed by picoseconds. So that kicking the analog solver, yeah, happens a lot. So what can we do? So although AMS is sold as a single engine, I don't know of any vendor that sells it as a single product. They're normally an analog solver, a digital solver, and there's communication. So the analog will have variables it can read and write to, similar as the digital one. The digital ones can read analog variables, but can't write to them. And similarly, the analog solver can read variables from the digital, but it can't write to them. You can use string data types. Try and avoid them in the analog domain. They're problematic, is the phrase. Whatever tool you go to seems to have issues with it. They weren't well defined. Out of module references to analog owned variables are not allowed. So this actually protects a lot of the analog stuff and makes it more robust. Right, then the next. So now we're going to go on to the UVM mixed signal bridge, which is really the crux of the change that goes into the UVM. So yeah, so the bridge is a module that will sit next to your DUT. In it, it's a system Verilog module, and the whole purpose of that module is to support the class-based stuff that needs to connect to the UVM world. So in there, we tend to have a proxy and a system Verilog interface. You have to have a proxy as a minimum. The system Verilog interface is optional. Then in there, we have an analog resource, and that is where you code up your the functionality based on the abstraction of the pin. So if the pin's a user-defined net type or a real or electrical, you have to make the analog resource match the DUT extraction. The ports or the connections from the proxy or system Verilog interface to the analog resource are done as out of module references. Loads of people go, why? System Verilog's really powerful, I can do all of that. Yeah, go to AMS, you've got logic and you've got electrical, and if you go to WReal, you introduce all manner of other problems, and when you start to go to bus ports, you're just going to go down a path that you'll be fighting simulator errors. So out of module references is the way to go. So the proxy, which is mandatory, it's got 4 main ways of communicating with the analog resource. One is it pushes a request into the analog resource to go and generate something, like please go and generate a sine wave. Something called a push sync, which is go and ramp up the supply to 5 volts and notify me when it's ramped up. Now, you might go, well, I'm ramping up in 10 nanoseconds, so I know. Remember, the analog solver's got tolerances on it, so it might not be.
It might be loaded.
Yeah, it might be loaded, yeah. Then there's pull, which is basically you've got some event in the digital that says, go and get me the value of the voltage on this pin. And then monitored signals, if you really need, is where it's trying to constantly look at the value in the analog resource and send it back to the UVC. But of course, in AMS, you can't do that. It has to be quantized. So, and controlling that quantization is non-trivial. So the system Verilog interface is optional. The idea is we keep that there for people who've got pure digital signals. They could use the system Verilog interface. It would go to the analog resource, and they would convert that to electrical if need be. And I've got some slides on that in a while. The pins on here, although I've got 4 pins, ref VDD, ref VSS, plus or minus, it could just be 3, you know, but the key thing is make the pins classed as interconnects, so they're typeless. That has a couple of advantages. It means if you accidentally try and assign to it in the mixed signal bridge, it's an elaboration error. So it's a way of trying to make sure people don't do things they shouldn't do. The ref VDD and ref VSS are really there if you're converting from a logic to electrical, you know what the voltage needs to be. I think that's it. So just as some extra things that we've had to do in UVM AMS or mixed signal is we've got a couple of extra includes. So we've got a package that's included in the bridge called the UVM-AMS package. There's very little in there. It's just neater to package it up than it was for people to do it individually. And then an extra include. And those includes we'll go through later because it's how all the messaging works from the module world. Yeah, and things like you could have a mixed signal bridge and in there a proxy that calls functions within the analog resource. What you've got to remember is System Verilog is really powerful, modern. Verilog AMS is quite old. Verilog AMS requires that there's an input to a function even if it's not used. So you have to replicate that in your System Verilog version. You have to go to the lowest denominator, which unfortunately is Verilog AMS. So what does the analog resource do? Well, for a logic signal, it needs to convert to what the dot pin extraction is. Well, if the dot pin is logic, all I need is a short to connect the two. So you can just use the alias command and just short the out of module reference to a wire in there to the actual analog resource pin. For something more complex, where you're maybe wanting to generate a sine wave, the classical approach, people who've got a digital background, is create a digital sample of a sine wave every so often, so you've got a nice step effect. Well, remember that every time you convert, you change that value and it goes to the analog solver. That's a D to A event. You're slowing down the analog solver. It might not even be using that sine wave that you're passing in. So, unless you're wanting to buy more licenses, it's just going to slow it down. So the key change is you place the generator in the analog resource. So you move your sine wave generation that you would have done in the UVC as a sequence of samples, and you pull all of that into the analog resource. So you generate it as a continuous sine wave in AMS, and you put your local way of doing it in System Verilog.
So instead, does that mean you tell the resource, I want to generate a sine wave this frequency?
Thank you, yes. Have you not seen these slides before? So yeah, so what we're talking about is basically your UVC will now say, I want a sine wave, handle the properties over like the amplitude, phase, frequency, DC offset. That goes into your analog resource, and that's where you generate it. So that's really the big change from the classical UVM that people are used to. And it's probably the biggest challenge in rolling this out, because most people will not grasp why they need to do it. And it's that D to A events. There are some other subtleties that, yes, if you put a steps changing there, you can get the analog solver to make a nice straight line in between. Again, analog solvers have lots of tolerances, so it's not going to be perfect. And you'll get harmonics appearing that you weren't expecting. Yeah, and it still honors everything that UVM stands for. With the way the test writer would write, they still write, I want a sine wave. It's just where it goes is slightly different. So I'm going to pass you over to Stephen, because all this class-based stuff is rather fancy for me.
So that to outline the need for the proxy class then. So what it allows us to do really is to connect some sort of relocatable UVM code into this analog resource and call into those, these functions that are going to be implemented in the analog resource to do whatever you need to do to drive the DUT, such as the sine wave generation, etc. So it is, it's only a thin layer to allow us to basically call out from a UVM agent to do something in the analog resource. And it also allows us to do this sort of relocatable connection between UVM classes and the static System Verilog module-based hierarchy. So if we derive a proxy class from something that we've called a UVM-AMS proxy, which is really just it's just a naming convention. That's all it is. It doesn't contain anything more than just being something derived from a UVM report object. Now, we go into details a bit more about why we derive it from a UVM report object and not just a straight UVM object, because it then means we can do some nice messaging. We can then leverage the UVM messaging verbosity control if we do so. So if we basically have the proxy class definition somewhere that's available in the EVM world, and then inside the SV bridge we actually implement this the class, and we instantiate it. That's the concrete class instance. There is a naming restriction we have on this __ UVM-AMS proxy simply because the nice macros that Peter has written actually use this to provide a messaging context, which we'll go into later on. So there's a sort of convention on the naming here. Then if you have this sort of system set up, then you can basically pass a handle to the proxy class by hierarchical reference in the test bench, and just put that into the UVM config DB, just the way that you do, exactly the same way you do is for virtual interface. So just to sort of go into the software design sort of pattern type, the proxy itself can be simply just an API. The proxy class from that you would extend in the UVM world can describe an API of methods that you can have, and then you can optionally implement them in different ways if you want to in the bridge module. So and then in turn the actual true implementation of those methods is done in the analog resource. So if we look at a traditional, this is showing you the architecture and extension of UVM-AMS to straight UVM. So we've got something there called UVM-AMS agent, but it's actually just a straightforward, canonical picture of a UVM agent with a sequencer config driver and a monitor virtual interface, which is connected to a read interface in the DUT via the config DB, for example. So then if we put the extensions on that we need, as Peter said before, we would introduce the concept of a proxy class inside the agent somewhere. That would then locate to a concrete instantiation of a proxy inside a mixed signal bridge, which in turn then actually communicates with the methods that are implemented inside the analog resource to do something in VAMs, for example, to generate your sine wave. So that's the sort of canonical picture of how the UVM-AMS sort of looks in comparison to straight UVM. So you can actually, it's quite possible using factory overrides. For example, if we located the proxy and the virtual interface inside the driver and the monitor separately, then to go from a UVM agent to a mixed signal agent, all we'd have to do is extend the driver and the monitor and possibly the transaction class to make that work. I think, yeah, there we go. So yeah, as Peter said before, the concept of the UVM-AMS and having the ability to communicate in the ways that Peter has described before means that we always have the proxy. And the other thing is that the proxy is there to support messaging. The SV interface is optional. That's essentially it's for logic drive. So if we look at the hookup of what we've described, some code snippets to make all this work, on the top left there, we've got a declaration of the proxy template. So we've got something called cap proxy. Well, this is going to be some implementation of something to do with a capacitor resource in our mixed signal bench, which extends from UVM-AMS proxy. That in turn extends from a UVM report object, which we'll go into a bit later. So that has some declarations of some functions in it. So we've got set capacitance and get capacitance. This is essentially just an API. We implement that by instantiating something inside the bridge module, which is just to the right of that picture, which will have, so if we notice our bridge there called cap bridge actually has something called cap core inside it, which is the actual analog resource. That's the thing that's going to do the work. In this case, it's actually an AMS model of a capacitor. Then the proxy declaration you can see in there, the class MS proxy, that has some declarations of some functions which get called by the agent, and they will then call via out of module reference into iCore. So they'll call the actual endpoint functionality of set capacitance and get capacitance. Then at the bottom we show how, so for example in the test bench, we can basically make a config database setting to set something in our env. So we've got the UVM testtop.env. We've actually got something called cproxy, which is actually sitting in the end, which is probably not realistic because we probably have this thing sitting inside an agent somewhere. And then anyway, we're wiring that up, or we're connecting that to this instantiation of this capacitor bridge and the AMS proxy inside it.
Yeah, so what was I going to go through here? These are, oh yeah, so push. So in your proxy class, you've got something like set RAM. It will call the function in the analog resource. Again, in AMS, all functions have to have a return value, even if they're not needed. So to cover that, I've put the void around the call there. So from there, I've passed in the values. Those change the internal variables, which then goes to the analog section because it sees it as a D2A event. And then I call set ramp there, which just is, I have to return a value. The other one is pull, where I've got a function to get the voltage, and I'm basically calling a function within the analog resource to go and get the voltage. In this case, it's an AMS one, so I'm getting the voltage between the plus and minus pins, which will be an interpolated value based on the last between the last analog time point and the proposed new one. Then the final one is a monitored value, where basically in the actual mixed signal bridge, you'll have an assign statement that will assign the value in the proxy with a value from the core. So what we've used is the AMS delta function, which tries to quantize continuous time signals onto a discrete variable. That discrete variable is read by the assign statement, and the assign statement shoves it back into the proxy, and so your agent can read it. Although you can do that, I really would question why you need to monitor an analog signal, because that can generate a lot of events. Especially it depends on how you've configured the AMS delta, but I have programmed them wrong myself and stalled the simulator.
Could you use maybe your analog resource to effectively do something that's kind of monitoring it as in an analog way, and they get the essential characteristics of the thing you're pulling back?
Yes, you could do. So that's the other thing. If you wanted to go, what's the frequency of the sine wave? I would do that in the analog resource because it's the domain that makes most sense. But there could be cases where you want that.
And then that might be you do it in a discrete fashion.
Yeah, I mean,
continuously.
For me, this is probably you do it for getting a trigger to say it's gone out of range or over current. Okay, now the push sync is a bit more complex. In AMS, when you change a discrete value, it goes through a transition filter. The transition filter will ramp up, but there's tolerances on when that will actually happen. I mean, pretty close, but it might not happen. So what we decided to do was create an end of transition variable, which would look at the discrete value you wanted, the output of the transition, and when it's below a certain value, assume that the transition is completed. Then that can go back to the analog resource to say this task has been completed. So you've got proper handshaking. You could monitor current, you could do other ways. So people have used hash delays and gone, well, I know it's meant to ramp in 5 nanoseconds, use that, but you're breaking the synchronization that you really need between the two engines. Yeah, and we just use it as a blocking call. So the next slide is quite involved. So
you're not doing that with a cross, because probably a cross would be an overkill way of doing it.
Yes. Yeah, and you can just do it more. I mean, if it's a voltage, the tolerance is going to be 1e to the -6. So
there's going to be a time point there anyway, so you don't really need to. There'll be a time point at the transition.
Yes,
you don't need to.
There should be, but you've got tolerances on it.
Exactly, but what I mean is you don't want to force yet another time point just to get an accurate cross.
Correct. So here we've got the proxy.set capacitance. I know it's a bad example, but it was just the one we used. And I basically want to change the capacitance on the fly and wait for that capacitance to have changed. So that proxy command gets pulled into the function that's in the proxy within the bridge. That then calls the function in the analog resource. The analog resource sets the values, and then it updates a value of cap end of transition, which is a discrete variable. That then goes to the register in the analog resource. That then is read by the function. That then goes to the local register, and that's where the wait command comes from. So I guarantee that that variable has been updated before the function exits. So I've made sure the synchronization is there. So it's quite involved, but it's robust, whatever happens. And then after the analog solver moves ahead, we've got something that generates an analog clock that just toggles. There are far more optimized ways of doing it. And then that will update the end of cap end of transition. That goes to an always block within the mixed signal bridge, goes to the register and back up. So there's many ways that this can happen. So as an example of how we might use an analog resource for different signals, you know, as I said, we want the analog resource to match the dot abstraction. We need all the out of module references that might be used for the AMS abstraction or the DMS abstraction to match. So it could be that you've got loads of functions that are needed for AMS, but in pure digital, you don't need any of them, but they just must all align. So at the top here, on the top right, I've got an analog resource, and I've assumed that the dot pin is discrete, it's logic. So I've got a wire input called D in, and basically I've used the alias command to short D in to D out, because there's no conversion needed. But I've had to leave all the functions and all the other variables that might be used for if the resource was DMS or AMS in there. Then I've got a dot which is using real number model or DMS, and basically somewhere in there you've got to do an assignment to D out as a real number, whatever modeling system you work. And then of course exactly the same in AMS. So the idea is the committee will provide some examples of this. Make caps, resistors, inductors are easy to do, maybe a voltage source, but they're going to be there as examples that you can take and work from.
So, last question now, but I presume you have to make your analog resource match the abstractions you're going to be using with your DUT.
Yes.
And potentially that could get complicated if you've got lots of pins, because you might have multiple.
So what you probably would do is do this either per pin, or you might group them together. So something like a USB where it's got a voltage and some data communication, you might do as a single analog resource, a single mixed signal bridge and agent. But my experience is if you've got 5 power supplies on the chip, normally they can ramp up and ramp down in any order.
Yeah.
So you tend to just create a mixed signal bridge for each one individually. Right. Hopefully we don't run out of time. Right, over to you, Stephen.
Okay, so I think as Peter said some time ago, one of the things that we need to do here is to be able to use UVM to basically set up our mixed signal DUT configuration before we start advancing time, before we start getting into the run phase. And that's for all the benefits of being able to randomize things nicely so that people can cover a lot of configuration space. So what we're proposing here is that we basically reuse, although we could actually create our own phasing schedule for UVM-AMS. We use existing UVM phases to basically have some rules about where we do a read, modify, write scheme. So we'd have, if we look at the table at the bottom there, so during the connect phase, we would use one of these get parameters calls to read the parameters from essentially from the bridge level into the relevant UVM agent configuration. So we have a configuration class which would then hold these representative variables which would be representative of these parameters. Then during the end of elaboration phase, then any test level modification that we'd want to do due to our sort of randomization of our test, we would then modify the parameters inside those configuration classes during that phase. And then at the start of simulation, we would then apply those agent parameters back into the sort of bridge world by calling the set parameters in the proxy. And then just the final point there on that slide is that the run during the run phase, there is, as I think Peter said right at the start of the simulation, you have to consume a minimum time step to allow the DC operating point to happen before you actually start driving anything from the digital domain. And we recommended a minimum time step there before starting the sequences. Next one, Peter. So I think that we're showing here in a bit more detail the scheme here where you would have an analog component which would have some parameters which will set some initial values. For example, here a decoupling capacitor value on an LDO output. So the MS bridge will then have the parameters in it which are copied into a UVM configuration during the connect phase, as we said in the previous slide. And then the test case overrides that configuration potentially if we choose to do that, and then you go back and set that in the analog resource during the start of simulation phase. So again, this is just showing a bit of a code snippet where we've got the read path back from the analog resource there on the right, which is the R series value going back into the configuration class. When we get parameters, you can see there they're making the assignment back into this configuration class, the item called resval that takes that value. And then when we later on in the phasing, we set parameters, that's the right path from taking a configuration that takes as a parameter the configuration class from the agent, and then we set the core R series to be whatever the item is in that configuration class. So that's showing just a code snippet of what it was going through in the previous slide. Okay, next one. And again, I think this is just going over the same, just showing in a bit more of a clear fashion what I was talking about there. So again, connect phase, we read the VAMS parameters into UVM configuration class. So this is being done in the connect phase of my driver. So I'm copying into the CFG class the result of calling proxy.get parameters. We have a handle to the proxy in a driver. End of elaboration phase in the test level there, you can see at the bottom. Then I'm basically going in and diving down into the hierarchy of my UVM componentry to set a configuration class, an R series value of 10K. And then during the start of simulation phase, then the driver then will call the set parameters inside the proxy class. So that will all happen sort of automatically as long as we adhere to this sort of setup in our agent. Okay, next one. And then the final one in the phasing spiel here is that the fact that we need to, first of all, when we get into the run phase of a mixed signal test, we need to first of all raise an objection, because if we start consuming time without any objections, the UVM test will say, well, nothing's telling me to stop, so I'll just stop immediately. And then we need to ensure a minimum time step is consumed such that the analog solver will get to DC operating point. And then after that, we'll say, okay, we've got DC operating point, we can start our sequences. So now moving on to the messaging requirements. So, you know, when we use UVM, we've got a nice mechanism to filter and control messages from any part of our UVM environment, anything that's a UVM component. You know, when we issue UVM info messages, then we'll get to know where it's coming from. The problem is with the mixed signal, particularly the analog resource, it's not part of the UVM hierarchy. It's actually in the module-based hierarchy. So you could still use, you know, some kind of UVM info, but you wouldn't know where that was coming from. It would just be coming from the sort of global space. So if we use a little trick to extend our mixed signal proxy from the report object, then we could use a set report handler to, even though that report object itself is instantiated inside the bridge, from the agent level, what we can do is say, okay, we'll make the proxy's report handler to be my context, and then it looks like all the messages coming from the UVM-AMS bridge world and even inside the analog resource will look like it's coming from the agent. So one of the tricks we use to do that is to actually, inside the analog resource, we're essentially calling the UVM info context macro. That takes a class handle as a report, which has to be a UVM report object, which is RO in red there, and that then passes messages back to that. So we also recommend to use a %m in the UVM message body to get the physical path, because although we'll see a UVM component path, we won't really know where that's coming from in the module-based hierarchy. So once we've done that, we can actually have some decent control, and we can switch on and off messaging and increase and reduce verbosity on a component-based basis, as we can in the rest of UVM. So here's we're showing how this setup works. So during the connect phase of a monitor, which has got a handle to the proxy, then we call set report handler for the proxy to essentially this dot get report handler. So the report handler of the enclosing UVM-AMS monitor in this case. So that means the messages coming out from the proxy will look like they're coming out of the monitor. And then inside the bridge, we can see we're calling the UVM info context macro. We're passing in the handle to the UVM-AMS proxy with a special fixed name there. So that will then send the messages back out essentially to the agent context, or the monitor context in this example. Okay, next.
So yeah, so how do we get a message from the analog resource? Because if I'm using Verilog AMS, I can't import a package. So I've got a problem. I can't use the UVM macro. So normally what happens with this is I go for a swim for an hour, and because swimming up and down lanes is boring, I have to have some problem to solve. So I put this as a challenge. So what I suddenly thought of is, hang on a minute, there's upscoping in the Verilog language, which means if it doesn't find a function in the local module, it looks at the next level up. So I decided, let's have a go at that. Let's see if it's supported.
Does it work?
Yeah, yes.
Does it work all the time?
It does work all the time, and all of this stuff we're showing today, how we've got example code that has been tried on 3 main EDA vendors that participate. So we've got that one include file, which is UVM_MS VAMS-H, which is for the Verilog AMS file. Basically, it's got some local params for the UVM verbosity settings, because you can't have enums in there, and this was the best way of doing it. Then we provide some macros, UVM_MS_info, so they look like the existing UVM stuff, but actually all that does is call a function that doesn't exist in that module, so it looks at the next level up. We've got exactly the same for the DMS one, but you must include the UVM package because I'm using the proper UVM verbosity enums in that one. And then in the main bridge, we've got another include, which basically also has the macros, so you could call the same ones there, but it's also got the definitions of the functions to then go and call the UVM reporting object. Yeah, now if you've got something that you want to report from the analog domain rather than the digital, it's a bit trickier because the analog solver cannot call functions that are in the digital. They're just not allowed. As a committee, we've looked at it, and it just becomes more and more elaborate, and the set of rules are then end up being 2 pages long, which no one will understand. So what I've done here is something that is a bit of a trick. I've got at the top there, I've got an analog section, and I'm basically, the I+ is me just monitoring a variable that's looking at the current on a pin. And I've gone, if it's gone above a threshold and this I thresh triggered hasn't triggered, I set it to 1. If it goes below a threshold, I set it to 0. I then use the AMS delta to monitor that integer, and when it toggles between 0 and 1, it will then trigger that always block. I format a message. You can't use sformat F in Verilog AMS. I wish you could.
So you can't.
Yeah, you can't. Yeah, that's a different story. So you have to form a message into a string. I know strings aren't really well supported, but that part does work. And then if it's triggered to 1, I basically call the macro, and I can use the UVM verbosity settings, and then that upscoping all works nicely. So over to you, Stephen.
Okay, so yeah, I think if we're going over, yeah, we're stating something here that we've already kind of gone over, but this is showing the snippet of code that you called on the previous slide, upscoping into the function that you've defined in your set of in your includes there. So it's actually calling UVM info context inside that function, and then we're providing this fixed name of the proxy to be the reporting object, and then we get the nice message on the screen at the bottom, which gives you so it looks like it's come out of this V agent, and you've got the message there. A couple of the things that we found with the current incarnation of UVM in terms of messaging for mixed signal is that if you're trying to print out you're trying to use the UVM printer to the print real functionality, it uses %f formatting, which isn't really appropriate for very small values. It's not the right formatting type. So we propose a change of using %e for that sort of thing. So you can have a better printing, because you end up with things that look like they're 0 and they're not actually 0. There is another issue with the time stamping of the messaging in UVM 1.2 onwards, in that the compose report message in the base class, it actually uses $time rather than real time. So although there's a proposed Mantis item UVM, we've got some, but essentially we override the report server, and for our mixed signal examples, and we fix that by using the real time instead.
So with UVM, there's many ways you could do the setup. The setup we are recommending, if you've got a mixed signal, is known as the dual top setup. And even the UVM committees tend to recommend this. So what we've done here is our test env is really your physical module-based hierarchy. Your test case is all the class-based stuff. This has a couple of advantages. If you go to hardware accelerators, you've got a nice clean split from the software layer and the hardware layer. The other thing is your test env could be a schematic. So you might need to handle that. And avoiding complex UVM code in a schematic capture tool is the best thing. And then, if you've got to change the abstraction of the analog resource in the test env, it's far easier for a tool if you can use a nice GUI to do it rather than text files. So this is just a recommendation. You don't have to do it. If you want to go into the complex ways, you can do.
So that means that you've got an instantiation of the test env might be a schematic.
It might be a text feed, yeah.
It could be a text feed. But then in AMS case, wouldn't you have to have an instantiation of the image bridge?
Yes.
As a thing.
As a thing, but most schematic capture tools can handle a package. So yeah, what I would personally do is I would make the test bench a system Verilog view, because there's no point in drawing a schematic of your test bench, because you're going to have so many components there, no one can read them. The ones I see drawn nowadays are, they're like A0, and you can't see what's happening, and nets aren't named. So just what will be provided. Now I've written them all. The package that you'll need to import into the bridge and the MS agent, and the 3 different include files needed for messaging. There really isn't that much to it, and the whole idea from the beginning was, let's make the minimum amount of changes possible. So that's, I've finished, so just about on time. I was worried about that. So questions, really. Well, you can mark this as the best presentation of the day. We've got example code. I can't send it to you, but if you go to your EDA vendor, they will have access to it and they can share it. Well, your guys. Yeah, we just need to strip the header off at the moment. But yeah.
So is it going to be released, or is it?
The standard is sitting on my laptop because I've written about 30 pages, and the problem is it's down to volunteers doing it. So I'll go on a Friday afternoon with the best intention of writing it, and someone will call me going, my sim's not working, and that's my time lost.
There's a question online.
Okay.
Are there any basic examples of UVM-MS as an open source which they can check?
Not at the moment. The examples I've written are on GitHub, but they're under the limited group from Accelera. It is shared with the EDA vendors, but the plan is to make some open source ones. But as I said, if you speak to your EDA vendor, you could get access to them. There's nothing in there that's proprietary.
So I did have one sub question. Is that did you? So obviously there's a part where you initialize the DC the DC operating point. Did you ever try it as a separate phase? Because in theory you could insert a phase, a user-defined phase before the run phase, and that would kind of make it to consume some sort of time. That would kind of make it seamless.
You could do, but if you think you've got all these people out there being taught in UVM, and you suddenly go, I'm going to insert another phase just for mixed signal.
Yeah, okay. Yeah, no.
I mean, the concept of moving your driver from the UVC into an analog resource is it's going to be hard enough. I mean, 2 vendors I've spoken to have said their biggest concern is that they're not going to get that message across. So
It makes massive sense. So
well, we had one guy on the committee who was absolutely adamant he could generate a sine wave digitally and run his sim, and he chose an example of 4,000 transistors and said it only took an extra 20% of runtime. What's 5 minutes versus 4? And I was like, yes, but that won't scale linearly. But he was, yeah.
We have a silly situation now where we have a current UVC, which we then try and convert. It basically generating digital signals. This is originally made to feed the digital, and then we're trying to convert that into analog waves. And you know the performance is pretty. And then we're mixing that with another signal to mix it up, and then the analog mixer takes it back down again. It kind of works, and we've got this, especially in Spice.
Just tell me afterwards what vendor you're using, and I'll just buy some shares. And it sounds like better than the guy.
I don't know. I think we'll go past before. I mean, we've got a lot of time into like a real number model, so that helps. But it's not ideal.
Yeah, and from a student point of view, this is mixed signal verification is non-trivial, and finding people who can do it is actually really hard.
Yeah, part of me coming to this is I think I've got a guy who I think could probably handle it. So they're far between, but yeah.
Well, they'll probably contact me on LinkedIn then later.
I was interested in the point made earlier on that about randomization. Of course, randomization isn't required for this, but it's a case of why people have an objection to it. They can cope with Monte Carlo, so why can't they cope with randomization?
I think it's because the analog, from an analog background, they're used to seeing a sine wave source. They know what's happening, and this is my experience. When you say I'm randomizing, they think you're going to literally roll a dice and configure the chip, and then they've got to try and guess what configuration it's in to test it. They've lost that step that you randomize some constraints. You've got access to those variables, so you know what's happening.
Yeah.
And also AMS tends to be more directed.
Yes.
So it's to try and tell them, look, you can do randomization, but you can also do directed. If it's me, I do directed. I don't know how to randomize. Yes.
There's a little bit of I find it difficult to check. There are some things that in the analog it's just easier to do with the visual check.
Yeah.
The analog, and I need to dump in front of an analog designer and say, is this okay? And they're not going to be able to. They don't want to look at my UVM check.
But you could build a checker that at least has bounding boxes on it, and then if it goes out, there's something wrong.
We always do both, right? There's always a nice Python plot.
Yeah, I wish everyone would supply all these nice things, but
We generally do it with when we're doing sort of outbound signaling or detection. We actually plot it on the waveform, so our predictors and our checkers actually plot their own thresholds that they're looking for as signals.
What you really need is on the monitor in the analog resource is an envelope tracker that basically is tracking the signal, and if the actual sense signal goes out, it's raised a flag to the agent to say, right, something's gone wrong.
And export that threshold tracker to a signal in your interface. Because when you debug it on the waveform viewers, you can see it. Engineers get very excited when they get the waveform.
But it's making that envelope tracking and all the rest is non-trivial, and then it's more stuff that a lot of most people who program in Verilog AMS, they're very simplistic models. They're not the sort of stuff I throw together.
Getting them to not use dollar display. Or even the worst one is when they're printing out errors, they just put dollar display warning.
Yeah, there's many improvements in there, but yes, as an example, my analog resource is about 4,000 lines of code to do some fancy stuff. So, you know, it's non-trivial, some of this. Anything else from online? No? Oh, they've all gone to sleep then. Yeah.
So when's the official release date for the spec?
Pressurising me last week.
When's T-Code due?
Yeah, yes. Yes, when are you going to do it, Peter? Yeah, I think they want it this year. I mean, I do work quite a lot with some of the people in Cadence who support a lot of it. So some of the examples I've written, they go away and do help clean it up and check things. But then I have to make sure it works in all the other tools as well, which can take time.
Yeah, Steve sends his apologies. He was very torn as to which one to come to.
Yes, you should know this anyway. Right, we're after past, so that's it.
Thank you, Peter.
Thanks, sorry.
Thank you.
Cheers, Steve.
Okay, thanks everybody. Cheers, Peter.
Cheers.
I'll log off.